Hey everybody, it's Dr. Jensen with CCJ 3701, Research Methods in Criminology. So we're just continuing on with ordinary least squares regression or linear regression. I'm going to show you, just overviewing briefly how the calculations work when we try to figure out how that line is constructed. So again, just by way of review, we talked about how if you didn't know anything about somebody, but you just had some maybe averages of something from other people, then you could use the average to try to predict what theirs would be. Okay. And then again, the line is going to try to better that prediction. Okay, so let me just show it to you in this way. Let's say I collected everybody's shoe size in the class, okay? And then we had a few more people add the class, and I wanted to predict what their shoe size was. I don't know it. And I said, well, how could I predict their shoe size? The closest thing I could do was take the average of all the shoe sizes I know, and they would probably, the new people would be near that average somewhere, okay? But that would be the very best I could probably do, the best prediction I could possibly make, okay? So to try to do a little bit better, it would be nice to know a piece of information about the new people. What if I wanted to predict their shoe size and then I said, hey, can you tell me how tall you are? If I had their height, I could get even closer at predicting their shoe size because there is a relationship between shoe size and height. And that relationship could be graphed by a line. With how many inches you are taller, you get this many more centimeters in shoe size. Okay, so that's all regression really does, is it takes this piece of information about you and tries to better that prediction at finding out that about you. That's it. And when it does that, it does all these little calculations to explain how close that information gets you to a hypothetical line and how it deviates away from that mean. Okay, so we want to know how much distance there is between our line we are proposing and the mean that we actually know. And that's what we call by deviation. Okay, so we look at, what's the deviation of the observation, or yi, from the mean? How much space is there? And we can explain some space, but there are going to be some deviations that we can't explain. Okay, so we try to capture all of that together, and through a series of calculations, I'm not going to go through these in detail, but we call these sums of squares. We square all those deviations we know, explanations that we can account for, ones that we can't, and we estimate those. And we take all of the total deviations plus the regression or explained deviations plus the unexplained ones, and that helps us eventually come up with our sum of squares, or how much variation is going on in the data, okay? The total deviation away from the mean. Once we know that, that can help us plot out our line to see how steep it is and where it starts to cross and stuff like that, okay? Some people used to calculate this by hand. Good for them. We're not going to do that, okay? We're going to let SPSS do this for us, but I wanted to just kind of show you some of what the formula is doing. It's actually trying to come up with all these little distances away from a hypothetical line and an average line of what the average would be. And that's how it's doing it, okay? So when you get your little ANOVA box, you get that sum of squares. You get what we call regression and residuals. Residuals are the errors, the unexplained deviation, okay? So that way we kind of are making a very conservative estimate of what this line actually is. But this is all the algebra and the math behind it, okay? So the mean square is what we call the average, okay? That's the variation of y. How much different is your answer on your shoe size from my answer on my shoe size, okay? And that's really all it's doing. But again, we don't report this box. This is just part of the calculation. Okay, let's go back up to that model summary box if we can. So remember when we get some output, you see r and r squared in that very top box. You've seen r before. We've used r when we did a correlation. Okay, so we need to talk about that one more time. So let's go forward. What is r? Okay, so remember when you run a correlation, you get a little r value, okay? It measures the association between interval variables, like how old you are and age. They're both quantities, how old you are in years, how much money you make, income, and we can actually get an r that describes how that relationship works, how strong it is, and how well it fits it. In a crosstab, we can measure association between two categories, like what is your gender, what is your religion. Okay, and there are other little tests you can run to get strength from it, how strong that association between those two variables are. So basically R tells us strength of linear relationship, okay? And that's how you run a correlation, how you get R, you go in the analyze menu and so forth, okay? And then we had this kind of handy dandy table that said you get in this R value you get, depending on what it is, if it's exactly 0 or it's between 0 and 1 or it's exactly 1 or it's between -1 and 0, that'll tell you kind of how the relationship works and how much it varies, okay? So you've seen R before. We call that the correlation coefficient. So it just tells you about that relationship. When you have R and R squared, okay, sometimes that value is really close and other times it's a little different. We actually don't use R when we do regression. We use R squared. The reason we do R squared is we've been squaring the data and we square the strength of the relationship to account for the stuff we can explain, the stuff we can't explain. We get a lot of negative values when we do these calculations, so again, the squaring counts for the negatives. But R squared, again, discusses the relationship, okay? We call this the coefficient of determination. So we say how much variation in y, or the dependent variable, can be explained by the model, or all the little variables inside there, the independents. Okay, that's why it's in the model summary box. So what is your model? Your model is your independent variable and any other variables, your predictor variables. So maybe you have like 8 variables you shoved in there. Any variables that you use to make a prediction, attempting to explain your outcome variable or the dependent variable, okay? So you could literally just have one variable predicting the other, x is related to y, or you could have this x and this x and this x all contribute together to try to predict y. So here's the example. We did the shoe size and the height, right? So I'm going to ask you what your height is, and I'm going to assume it's related to how tall you, or excuse me, your shoe size, okay? If I wanted to get an R squared on that, it would probably be really close to 1, like a 0.9 or a 0.95, meaning it's almost perfectly you can predict someone's shoe size based on their height because of biology having really good, strong relationships between each other. Okay, what if I knew more than just your height? Okay, and I want to predict your shoe size. What if I knew your height and I knew your shoe size when you were 5 and I also knew how old you were? Because, some people shrink when they get older. That would give me even more information, more and more independent variables, more x's that I could use to predict your y or your shoe size. Okay? So the more information you have about somebody, the better you get at predicting what happens to them. Okay? So that's why we like doing these multivariate models. We want to know as much as possible to get the very best prediction of what happens. And we call those control variables. Well, I not only want to know this about you, I want to know this and this and this and this because I think it's going to make me better at predicting what happens. Okay? So when we get an R squared, it tells us how well all those variables do at explaining the outcome. So how do they do? How much coverage do they get of shoe size? How do they contribute to predicting shoe size? How much variation is being explained in shoe size? How much do we get? That's all R squared is, and we're going to practice doing this together, so don't worry too much about it. Okay? Again, we've kind of showed you some of the math behind this. Let's go into the other box that's really important in your SPSS output, and we're going to run some in a minute so you can see it in action. What are the coefficients? The coefficients box, really there's only 3 things to pay attention to in this box. You have the constant, or we call the intercept, the point of the line which, crosses the y-axis when x is 0. We also have b, you see a big capital B inside that box. That's the slope. So the amount y changes with a increase in x, and it's always an increase. And then we have the significance level, right at the very end, the far right part of the box. Okay, those are the 3 things we use to write up when we get a result. Okay, so those are the 3 things to pay attention to. So again, constant is the y-intercept. We call it the regression coefficient, or the b is the slope, how steep it is, and then whether or not the whole thing is even significant. Does it actually predict each other? Okay, so that's what you get in SPSS. Okay, so there's a lot of really complicated math, and we're not going to go through this, but this is the actual formula when we try to calculate the slope. Okay, some people do this by hand. That would drive me nuts. And you can see why when you're working in a big organization, no organization is going to sit there and wait for you to do all this algebra and hope you don't make a mistake. That's why we use statistical programs like SPSS and so forth to do this for us. Okay, that's just too much. Okay. You do get a t-value. It's actually a test of the regression coefficient. It tests the probability that the coefficient is not zero and also gives you your significance level. We never really report the t-value. It's not meaningful in and of itself, so you don't have to worry about that little t. We really just report the significance level. Okay. We also have standardized coefficients, which kind of tell you how much each variable is contributing to the relationship, but we're not going to do a lot of that in this class. So I'm going to go ahead and jump into SPSS and show you what this starts to look like when you run stuff. Okay, so in here, I'm actually in the law enforcement data that you've used maybe for some examples from last week. It's in your R drive and our courses folder. Okay, you'll find in the data folder. We're going to run an example really quick of how this works. Okay, so let's say we wanted to predict budget. Okay, and we wanted to know if we could predict your budget by knowing your employees. Well, we can do that. So the way we run a regression is we go to the Analyze menu, and then we go to Regression, and we select Linear. Once you get into this menu, you can put in your variables. Okay, so we're going to select from this data set a variable called OpBudget and put that in the dependent box. And then in the next box, we're going to put how many full-time paid employees you have. And that's what we're going to put in the box right underneath, okay? It's called block 1 of 1. Okay, that's where all your independent variables go. So that's the regression we're going to run. Once you have both of those variables in place, we're going to try to use your employees to predict your budget. Click OK. Okay, so you have kind of some info boxes up here. You don't really need to pay attention to those. Here's that famous model summary box that has the R squared in it. Here's the ANOVA box, okay? And these are really big numbers, by the way. And then at the very bottom, you have a coefficient box. Okay, let's start at the coefficients. First of all, are these two things related? That's the very first question you can answer. Look at this significance level over here on the end. Yes, I have triple zeros, meaning I have less than a 1% chance of this being false or being untrue. So it is a highly statistically significant relationship knowing someone's employees being able to predict their budget. So we go, okay, well, that's all fine and good. We assumed so much. What else can we know? Well, we know that on average, the average budgets we're talking about are about $2.5 million, okay? So this constant is Y. It's total, and it even reminds you what it is. The dependent variable is total operating budget for the 12-month period that includes September 2007. So it's basically their last fiscal year, okay? So the average starting point for these organizations is about $2.55 million. Okay, so that's what would be like the average. That would be what we would predict their budget to be if we knew nothing about them. Okay, the coefficient is underneath it, this 85,909. That's the coefficient or the slope of the line, how steep it is. So basically, with a unit change in X, we get this amount of money change in Y. So here's X over here. It actually tells us number of actual full-time paid agency employees. Okay, so a 1 unit change in X would be with every additional 1 employee, this is what happens to Y, or the budget. You get an extra $85,909.85. So basically, on average, with every additional employee, the budget increases to $85,909. Which makes sense when you think about salary and benefits and workers' compensation and liability and payroll taxes and all the kind of stuff that come with hiring a new person. Okay? So not only do we know, is this a relationship? It is. We also know how the relationship works, that basically every additional employee you get another $85,000. Okay? So now that's a great relationship to talk about in your result. Let's go back up to model summary where we look at R squared. Okay, R squared, it says 0.896. Okay, it's always going to be between -1 and 1. Okay, or in this case, 0 and 1. So basically, how much coverage of that dependent variable do I get by knowing how many employees somebody has?